All right, so we're going to keep going with these examples. Now we're going to look at the reflection matrix. Which is R equal to 0, 1, 1, 0. Okay, and we're going to solve the eigenvalue problem again, which is you need to define the problem of R minus lambda I over here. So this will give you what? 0 minus lambda will give you minus lambda, 1, 1, and minus lambda. Okay, so from this equation, we know this needs to be equal to 0. We can determine the characteristic equation, which will be the determinant of R minus lambda I equal to 0. This is the characteristic equation. We give you what? So it will give you that the determinant will give you minus lambda times minus lambda will be lambda square minus 1 times 1 will be equal to 0, which will mean that the two roots, lambda will be equal to plus minus 1, because lambda square will be equal to 1, no? Yeah? All right, so now we need to solve for the eigenvector. So we first solve for lambda 1 equal to positive 1. We first do the, yeah, it's fine. Generally we do the lowest one, but in this case, shouldn't matter. So we get R minus lambda, the identity matrix, will be equal to what? Will be equal to minus 1, 1, 1, minus 1, x1, x2 will be equal to 0. Okay? Or we can just rewrite this as minus x1 plus x2 equal to 0, x1 minus x2 equal to 0, which will give you x1 equal to x2, so that the first eigenvector corresponding to the eigenvalue of 1 okay, will be equal to will be equal to 1, 1. We do the same thing for the second one, so lambda 2 equal to minus 1. So this time we're going to get R minus lambda I equal to, so will be minus 1 will be 1, 1, 1, 1. Or this will give you x1 plus x2 equal to 0, x1 plus x2 equal to 0, which basically will mean that either x2 equal to minus x1 or x1 equal to minus x2, it doesn't matter, which will give you the second eigenvector. One minus 1. Okay, so all this stuff that I did is because if you look at the eigenvectors here, for the reflection and the projection, what were the eigenvectors we had for the projection? It was exactly the same ones, no? Okay, so all this stuff I did is just to show that to note that the eigenvectors for P, which is the projection, and R, which is a reflection, are the same because the eigenvalues are related by R equal P minus the identity matrix. So basically, what was R? If we look at the figure here, R was 0. What we find here, 0, 1, 1, 0. The one for the projection, we had 1, 1, 1, 1. And this one should be what? This should be 0, 1, 0, 0, 1. Okay, so you see you do 1 minus 1, 0, 1 minus 1, 0, no? Okay. All right, so now the last example I'm going to do is to show, to realize the definition of the eigenvalues. So the eigenvalues, what? It gives you the direction of a vector. It gives you the general direction of where you need to go, okay? But it's not going to give you the magnitude, all right? So let's see what happens if we do a rotation. So let's see, 90 degrees rotation. So let's call this matrix Q. This will be equal to 0, 1, minus 1, 0. Okay, if you think about it, if you have one component like this on the x, will be just by doing this, no? X, 0 minus 1, no? Okay, it'll be the same thing. All right, and let's see what happened with the eigenvalue problem. So we had Q minus lambda I equals 0, which will mean that you will have, I think we can do it at once, okay? What, this gives you what? So we'll give you 0 minus lambda, should be minus lambda. One, yeah, I'm just looking at my notes, I have something different. So, and then you will have here minus 1, and you will have minus lambda. Okay, so this will just give you, okay, we have this matrix. So now we solve the characteristic equation. This will be the determinant of Q minus lambda I. This will be the characteristic equation, which will give you lambda squared plus 1 equal to 0, which this will mean that lambda needs to be equal to lambda squared will be equal to plus minus I. Oh, instead of saying lambda squared equal to plus minus 1, no? Let's write it under this form. So here, let's stop for a second. All right, so anyway, this, you were right, I put this one because I was going to put lambda squared equal to plus minus 1, okay? And then I forgot to remove the square. All right. So here, the only thing I want to say is that imaginary eigenvalues have a physical meaning but are out of the scope of this class. So basically, the only reason I did this example is because what is the definition of eigenvalue, eigenvectors? It gives you the general direction of where you need to go, okay? So basically, if you think about a vector, it gives you the direction, not the magnitude. So when you do a projection or reflection, if you think about it, it can be more or less the same, depending how you want to look at it, okay? And the way you look at it is by the identity matrix. But now if you rotate, this is not going to give you the right direction anymore, no? Because you are rotating. You can make it give you the general direction, but it's out of the scope of this class because it will take too much time to really go through all the details about this with the eigenvalues, okay? And it's not really the idea. Remember here, the idea is to define the stress tensors with initial notation, okay? Define tensor with initial notation. Then we can define projection or movements, deformations, because then we're going to move to stresses and strain, no? Okay? So the initial notation will help us to give us the equation, and you know the stresses will be rotating and moving. Okay? All right, so I think that's it for this part of the chapter. And obviously, the next thing we're going to do is stresses. So these two pages were 51 and 52. All right, so chapter, I think this would be chapter 3 or 2? Chapter 3 will be stress principles. Okay, so finally we get to really what is the topic of this class, okay? All right, so over here, let's say consider the body shown below. So basically, we're gonna have to define a coordinate system. Say x1, x2, x3. So if you want, x1 will be x, x2 will be y, and so on. This follow the right-hand rule. So in this, we could define a body. So it would be part 1. So a body that is subjected to all kinds of forces. To external forces. Okay, and let's say this one will have be here, which would be the center. So it would be like having mg. Instead of mg, we're going to call it density times p, okay? Like all forces, basically this is the equation that will be equivalent to summation of forces acting on this body should be equal to ma, no? Okay? But here, since it's per unit volume, mass will be given by the density, and this will be like body forces, okay? This would be like G, the gravity over here, and this could be moving, all right? So let me write that down. So if you want, this will be density. Since you don't really have a book, even though I give you PDF, and B will be the body forces. Obviously, you can have body forces on the three directions. Okay, so now if I take that figure and I make it a bit bigger now, so remember Newton's law, when you want to make Newton's law is only valid for external forces. And I want to make sure when you do summation of force equal to 0, that summation of forces only indicates external forces, okay? If you want to know what happens inside, what do you need to do? You need to break the structure so that those internal forces like stresses become external. Same thing we do with the boundary conditions, no? You report like simply supported, but if you remove the simply supported form, you need to replace that little triangle by two forces, no? Okay, clamp by two forces at a moment. So this is the same thing. So now what I do is I'm going to slice it here by the cut. So we're going to get just half of it. All right. So I'm going to look here at point P over here. Okay, and that little area over here, that will be delta S for the surface. So I cut it and I see what's going to happen in that little area, and then I will integrate around. So over here, what can you have? You will have a normal vector n sub I that will be perpendicular to the area. You will have forces acting to that area, and you can also have moments, no? Okay? So measure of moments equals to I alpha, so measure of force equals to ma. All right. So now, this is a guy that did a lot of work on stresses. So Cauchy postulates that the stress tensor T sub T upper n hat, so T n vector, so perpendicular to the surface, remains unchanged for all surfaces passing through point P and having the same normal vector n hat. Okay, so now this is classic solid mechanics, but you know, we start putting a bit more difficult, so it will be this. So if we now look at the other half, the other half will be like somewhere here. Really, we only need one, but. Okay, so we have this. Here it is still subjected to external forces, external moments, everything you want. We have point P over here. So point P we have normal stresses that should be perpendicular to the surface. And we have shear forces that will be tangent to the surface. Okay? So what we get over here is the overall stress tensor. Here will be Tn, okay? And because of the equilibrium, if you look at this one, if you want third Newton's principle, action reaction, no? If you have this one here, in this point you have one equivalent in magnitude, but in opposite direction, that should be T sub n. Okay, that's basically what it means. Okay, and here, it's going to be too much on the same figure, but you still have over here the rho b, okay, which is the mg at that point. So I'm not going to write it down, but basically the consequence of this is that on the other side, in order that you still have the equilibrium condition, you need to have this one to be opposite direction, but equal in magnitude, okay? Okay, so now, assuming, and this is an important assumption, assuming a very thin volume for which variation of forces and moments are being ignored. So be careful because this is extremely important. So basically what I take here is a very thin element okay? So this would be your delta S, in which we're gonna have here T sub n, and this would be here minus T sub n, right? So that if in that little strip we do summation of forces equal to 0, basically the only thing you get is Tn delta S minus Tn delta S is equal to 0. But what happened is this wasn't that thin. Let's say one side was a little bit thicker than the other one. This will induce some type of moments, no? Yeah? So then this assumption will not be valid anymore. And that's what happens. Sometimes you look at different theories of structure, like stretching theories and so on. And that's what they do, is that this assumption is not what is used. So the Cauchy assumption, what is assuming is that when you take a small element, basically is thin enough that you need to ignore the effect of forces or bending moments. More than forces, the one of bending moments that might be created. Okay? But that is not the case every single time. And that's another big assumption is like, for example, other equation that you derive in structures what is the main assumption they do every single time? These structures are thin, okay, compared to the length. And what is that? What does that mean? Is that the main deformation of that structure will be due to bending. If it's thick and short, what would be the main deformation? Should be shear, okay? Think about it, like when you think about deformation, think about how would you break it with your hand. If you have something long and thin, how will you try to break it? Bending it. If you have something thick and short, how are you going to try to break it? In shear, okay? So all the equations that you have derived in structures are for what? For what type of structure? The first one, for bending. So be careful, because if you have something in shear, 100% in shear, really all those equations are not that good anymore, because they are based on what? They are based on this equation here, that the thin, you have a very thin volume for which the variation is this. So this is from where the assumption of thin structure is coming from. Otherwise, you need to start taking into consideration that if this was thick, it would be, the forces here would be creating a moment about the center line. Okay? If it's thin enough, it's not going to be creating a moment about the center line. All right. So again, I'm going to say the same thing. So more comprehensive. Stress theories. Are available, but once again, but not covered in this course. But I just want you to make you aware of that. There's multiple theories about structures. Everything we do generally is thin structures, but you have a full theory which is just for shear. Okay? For very thick structures. Okay, so now let's talk about the stress tensor. So this is the most important part over here. All right, this is very important conceptually speaking. So we're going to talk now about the stress tensor. Okay, so Cauchy stress tensor, or Cauchy's law, or Cauchy's stress tensor, say that T I of N, we're following that notation, this different notation, equal to sigma ij nj. So here, be careful, because remember I call one sigma, the other one is tau. But what would be here, the sigmas would be 1, 1, 2, 2, 3, 3. The taus will be 1, 2, 1, 3, and so on, no? Okay, the one that will be tangential. We're going to look at that now, okay? So T, so in here, T I N is obviously the stress tensor. Okay, but here, since I put a bar over here, this is also a vector or a matrix. Sigma ij is the second order stress tensor field. Basically, second order because you have ij, no? Okay? And n is just a normal unit vector. Okay. Okay, or in full, what would be the vector? We have T1, T2, T3, maybe I shall leave some space, and 1, and 2, and 3. If it gets confusing, guys, with the notations from now on, if you let me, if you want, instead of writing with the stick markers, I can bring a normal pen. Or is it okay? Can you follow with this? Sometimes you don't have a hard time to read my indexes. So with this. Okay, so if you want next time, maybe I can bring like a normal pen. It will be thinner, it will be easier for me to put the indexes. Because even that way, sometimes I have a hard time reading them. So it should be sigma 1, 1. You can remove all those hats, but since I put them on the equation, plus sigma 1, 2, and 2, plus sigma 1, 3, oops, sorry, and 2, plus sigma 1, 3, 1, 3. This will be sigma 2, 1, and 1, plus sigma 2, 2, and 2, plus sigma 2, 3, and 3, sigma bar 3, 1, and 1, plus sigma bar 3, 2, and 2, plus sigma bar 3, 3, and 3. I have a hard time reading the indexes, so that's why I'm saying that. And okay, so basically this is, you have done this derivation in structures, I'm pretty sure, or at least you have done in solid mechanics. All right. Let's do it, it's important, so. Okay, so by considering a small piece of the solid in the shape of a tetrahedron. Maybe it was a long time ago, but you should have done this derivation. So let's see, for x3, x2, x1, so this is your tetrahedron, that would be ABC. So this would be your point P over here. Okay, so now it's going to be difficult to sketch this. All right, so, all right, let's say surface B, so we go B, P, C, is this area over here, no? Okay, so we'll call that one ds1 will be equal to n1 ds, where n will be, I don't know, to plot it, would be this one over here. Yeah, should be at the back. Don't know about too much. Now, so it will be the surface B, P, C. Now we can look at the surface. CPA, so will be the one going over there. So CPA. It will be DS2 will be equal to N2. DS, so one, this will be N1. Should be like N2, no? Over there. And now N3 should be like the one at the bottom, like surface ABP, all right? ABP or APB, doesn't matter. DS3 will be equal to N3 DS. Okay, so we have a general vector. So now imagine you have the face ACB, which is the general surface, no? Okay, so if you want on surface ACB, you will have, I'll put this. You will have your general vector or stress tensor T of N. Okay, I don't know how to plot now. It's going to be too much on that figure. But. Okay, so this one over here, if I needed to plot the stress, this one will be, you see, this will be on the area A, B, C. Okay, so what I'm just trying to say is that this stress tensor, which is on the area A, B, C, you should be, if you want to think about it, you should be able to break it into the projection on the CBP, no, plane, CPA plane, and APB plane. Yeah, would be like the X, Y, and Z. So if I kind of plot that, because this is going negative, this will show like, this will be here minus T and 1, because it's going negative, no? This is just for the sign. This one will be on this plane here. We'll have something like minus T and 2. And here we kind of have something similar, minus T and 3. Okay, and you can put vectors on this one, since we put on this one as well. I mean, the stuff is easy to understand here. So now if we do the summation of forces, so the equilibrium for the tetrahedral, what we're going to get is T of N ds. Wait, what is ds over here? Ds will be, let's see, so ds here is what? Ds is ABC, no? Surface ABC, okay? To be specific. So this will be equal to what? That constant here minus each one of the projections. So it will be minus T and 1, which will be on ds1 minus T and 2 on ds2 minus T and 3 on the surface 3. Yeah, this one will be each one of these surfaces. So ds1 is BPC, ds2 is CPA, ds3 will be APB. Okay, and this should be equal to 0. So This is going to tell us that t to the n ds is equal to 1, would be equal to t n1 n1 ds1 plus t n2 n2 ds2 plus t n3 sorry, you remove the S1. You don't have S1, S2. It becomes S. And 3 ds. So you can cancel all those ds. They don't have subindexes, this one. I just substitute by these expressions. Okay? So this should give you that t of n should be equal to t n1 plus t n2 plus t n3 which basically is what we were expecting. It's like this, or in indicial notation, we have tj of n. Here I'm going to change a bit the notation in order to make it will be equal to tj. So this is t1 of, I can do it that way, of n of I n of j. So now what I'm saying is that recalling the two equations we derived, which basically are, the first one was t I of n equals sigma ij and j. And the second one I call t of j n equal to t j n I and j. That's the way I wrote it. Or I put the parentheses in this one. So let's put the parentheses. So the above equations are equivalent. So I'm going to expand it so it's more clear. Are equivalent to what? T of n equal to t of n1, t of n2, t of n3 equal to t1, it'll be a nightmare. T1 and 1 and 1 plus T2 of N1 and 2 plus T3 of N1 and 3, and same thing for the others, no? Okay, so it will be T1 N2 N1 plus T2 N2 N2 plus T3 N2 and 3. So good luck reading the indexes here. And Tn3 will be T1 N3 N1 T2 of N3 N2 plus T3 of N3 N3. So all this stuff, all this notation is complicated. That's why I'm trying to go to something that makes more sense to follow. Or in matrix form. Or what that means that you have T J of N equal to, oh, okay, I did not have the parentheses here, so sigma ij, you can put them or not put them, and j equal to n1, n2, n3 times sigma 11, sigma 12, sigma 13, sigma 21, sigma 22, sigma 23, sigma 31, sigma 32, sigma 33. Okay, so now if I put it into a cube, all right, so let's see if I can find something. Okay, I do the figure and then I'll go back maybe to, oh, I think I have it here, or not. Yes. Okay. I think it will be part of the homework, but I mean, let's do it here. So basically what is showing this is that this will be the normal stresses. Sigma 3 will be on this face. This one should be sigma 2, and the one in this face should be sigma 1. So now this one will have a stress in which phase? This is on which phase? Remember the first index here, ij, this is the, if you want, the phase, no? On which is acting, and this will be the direction. So for the shear stress, this will be sigma 3, 2. Okay? And this one here will be sigma on phase 3, 1. all right? So we do the same thing here. This is acting on phase 2, no? It's going in the direction 3. It will be 2, 3. And this will be phase 2, direction 1. And this one here should be phase 1, direction 3. And then we should have phase 1, direction 2. So those should be the shears. Okay? So for example, so stress tensor at P is given by so sigma Ji I have here equal to 21 minus 63, 42 minus 63, 0, 84, 42, 84, and negative 21. Okay, and you have that to be on a tetrahedron. So x1, x2, x3. So again, it's the same as before, but this time A will have the coordinates 1, 0, 0. B will be 0, 1, 0. But C will be 0, 0, 2. Okay, not to make a unit, just to change. So the question here is to find stress vector having unit normal vector n equal to 1/7 of 2. Can I just put this E1 now for the unit vectors? I can put N1 again, but changing the books is given this way, E2 plus 6 E3. Really is the same, no? The same, it doesn't matter. Okay, and B, find stress vector on plane ABC. So that's when you need to find the equation of the plane, no? Of the plane, you need to find the equation of the plane going through points ABC, which is what we did at the beginning of the semester. Okay? So the first part is very easy. Let's do the first part and then we finish the second part. So solution. Part A. So we know that Tn, the stress vector, we just say is equal to sigma ij or jn? What did I do here? It doesn't matter because it's symmetric, so it doesn't matter. So sigma ij n sub I. And we said this was equal into the matrix form as what? Where's page 55? 2. I have it here, but I just wanted to find it. No, find it. Oh, here it is. So it will be a matrix form will be equal to this expression here. Okay, that's the one I'm trying to write, no? Okay? It will be equal to n. So you want a n1, n2, n3. So it should be a vector times the other components that will be, so even if we revert here, should be the, so 21 minus 63, 42, minus 63, 0, 84, 42, 84 minus 21. Okay, so this n over here is given by what? This n is really this one over here, no? Okay, so really this is equal to the 1,7. We can factor out the 1,7 out of what? Of 2 minus 3 and 6. This would be the direction of this vector. And then you need to do the one of all this stuff over here. So 21 minus 63, 42, minus 63, 0, 84, 42, 84, minus 21. Okay, so this will give you what? This will give you the vector t of n that we have over here. So what should be the first one? Should be, you do this one, plus this one, plus this one, no? And there's one, you do this one, plus this one. And this one, plus this one. So I have the results over here and you need to divide by 7. So I'm not. Best thing is to take MATLAB and do it. All right? I just tell you how to do, you do, basically you do line, column, no? Line, column. So this gives you a matrix which is 1 by 3, 3 times 3. So you end up with 1 by 3, no? Yeah? So you end up with the 3 components here. That should be the Tn1, Tn2, Tn3. And those 3 components should be 69, 54, and negative 42, which will be, or if you want in, if we expand it, should be 69 E1 plus 54 E2 minus 42 E3. But I'd rather have it under this form. And this T over here, just to make sure, what are the units of that? This is force. Remember, we are calculating everything with respect to the area, no? So it should be here per surface or area. Okay? So next time we finish part B, because it's going to take a bit longer because we need to find the equation of the plane. Okay? Once you have the equation of the plane, what do you need to do? You need to find the normal vector to the plane. And basically, we just substitute into the same equation. Okay? So it will be one extra step, find the equation of the plane going through A, B, and C. You find the equation of the plane, you can find the vector that is normal to that plane. Correct? Once you have the vector normal to that plane, we just apply the same equation again. So you can have the value of the stresses within that plane. And you could make any cut, okay? As we do through any plane. All right, so I'll stop over here the video for today. And I will try to grade your second assignment or third assignment this afternoon. So